Thank you everyone for joining, and today I would like to share a webinar with you about drivetrain electrification in Simulink. I'm Bence and I'm an application engineer here at Gamax Laboratory Solutions, and I'm going to present this webinar for you. If you have any questions, you can reach out in the chat window, or you can drop me an email later at the email address you see in the bottom of the screen. But for this webinar, we are going to talk about drivetrain electrification, and I would like to highlight the agenda for you, what we are going to cover today. So we will start with the challenges of drivetrain electrification in the beginning, and then we will continue with the electric drivetrain modeling in Simulink, and I will show you what options do you have to reach your goals in Simulink. And for this, I have brought you two examples. First, an EV battery modeling use case, where we are going to take a look at battery sizing options, and then I will go into a more detailed model where we are going to model a battery management system of electric vehicles, and I will show you how one use case of battery fault detection. And in the end, we are going to summarize everything, and we will continue with the Q&A. So if we want to talk about challenges of drivetrain electrification, we will have to take a look at the trends what are present in the drivetrain electrification market. So on the right part, you can see a market forecast for the European region by 2030. And you can see a figure there. With dark blue, you have the internal combustion engine market share, and rose color represents the mild hybrid vehicles, and the light blue represents the plug-in hybrids and the electric. So you can see that from 2020 until 2030, the segment of classic internal combustion engines or ICEs is vanishing in the sale of new cars. And you can also see that the electric getting more and more focused, and they will be the majority of the new car market. The mild hybrids are also important, and in 2025 they will represent the majority on the new car market, and they will take up around 20 and 30% by 2030. So we can see that the whole industry is changing, and we have a pretty big ramp up in the new car sales regarding electric vehicles. But this is nice to see, but there are some success criteria that have to be met for the drivetrain electrifications to be ready for this big leap in the next 10 years. So we will need to maximize the range of the vehicles. So you are mostly familiar with the ranges that you see now of the electric vehicles. They are reaching up to 600 kilometers maybe, but this is not enough. We will have to go further, and we will need to reach towards 1000 kilometers. Another big success criteria that have to be kept in mind is that we have to ensure the safety of new technologies. So you could see electric vehicles that are not that safe right now. Sometimes the batteries are exploding, the whole car is getting on fire, and this is not what you want to experience there. So this is why we have to keep in mind the safety as well. And we will need to define the limits for batteries and motor in a way that we can all reach our destination in a safe way. And the third main success criteria is that we will need to keep the dynamic characteristics of vehicles. So the 0 to 100 acceleration, for example, or the maneuverability of a car, suspension dynamics, that all have to be kept as they are right now, or they even have to be more advanced. This is maybe the less challenging, but we will need to keep an eye on this as well. So what are your options for reaching your goals when it's about electrification of drivetrains? So you can either go with a full electric drivetrain, or you can choose a hybrid configuration. So with a full electric drivetrain, you have many options to go with. You will need to choose the best location for the motor. So whether it is a front wheel drive, a rear wheel drive, or you have motors on both axles. And if you decide to go with a hybrid configuration, you will have to consider variants of single motors, or you will have parallel hybrids, and this is what you will have to consider. And in a hybrid configuration, you will have to choose the best location for the electric motor of yours, and you have many options for this, as you can see on the picture below. So you can have the motor between the ICE and the electric motor and the clutch, or you can have it between clutch and the transmission system, or even before the internal combustion engine. So you have 4 options there based on your location. So if we calculate everything and sum everything together, with the fully electric drivetrain, you had 3 options, and with the hybrid configuration, you have 4 options. So that's now 7 options that you will have to face and you will have to choose from. And you also see other challenges for your components, and mainly they are component selection and component sizing. And once you have the component selection and the sizing done, you will have to take a look at the vehicle performance analysis and optimization. You have to answer questions like, how do these selected components work together? Or how does the vehicle perform? And you also need to take a look at the charging infrastructure related challenges. Those are the range and the charging times and so on and so on. And for those bunch of challenges, you will need to calculate many things, and you will need to face them, and you will need to answer those questions as quickly as you can. And for this, model-based design can be really useful for you, because with model-based design, you can address the challenges that are involved in your development of your automotive systems. So how you should imagine model-based design? In a real life configuration, you will have a car with an electric motor, a battery, you will have the wheels and the suspension model built, and you will have also a transmission system or gearboxes, and you will have the controllers. So in a real configuration, you will also have the same components in your models and in the model-based design approach, but you will take everything and you will create a virtual copy of them in Simulink. And basically you will bring everything inside one environment, and you will have a model which will be the core of your development. And you can link the requirements and your specifications to this model. You will be able to run the system simulations. You will be able to test the models continuously during the development cycle. And once you have everything prepared, you will be able to implement the controllers that you have developed, and you will have automatic code generation for this. So using model-based design, you can address all the questions that you have during the development, and you can also be really quick, because in a virtual world, you can try all the configurations that you want, and you will be able to get the answers really quickly. And if you decide to go with the model-based design, you will start the electric drivetrain modeling in Simulink. Let's take a look at what options do you have for this. You can start from a blank model. So this is when you open up Simulink, you have a blank canvas, and you start building your components, you put everything together in a system, and you start simulating. So here you will have a really big flexibility for the design requirements, that you can tailor everything to your needs, but also building such complex models as a vehicle, it will demand high capacity and expertise. And all your problems must be handled internally there. And as you are working with a complex system, it will be time consuming for you. And if you have to waste time on modeling and you cannot concentrate on controller design, for example, you will lose the advantage on the market. So this is why we have the electric vehicle reference application built in inside Simulink. So you can have a solid starting point for your models, and it also ensures fast running simulations for you. And with this, you have many options for integrating your own algorithms. So you can really focus on your specific task, and you do not have to handle the whole model design and development. And it also has really good readability. And with all the parameters, you can configure the vehicle as you want and tailor to your needs. And once you have everything set up, then you are able to work with this reference application. And if you want to move further, then you have the virtual vehicle composer. And this comes with all the advantages of the electric vehicle reference application. And you can also parameterize each component of your model, and it uses a robust modeling technique. So later, if you want to switch something, or you want to change one parameter, you can do it in a model, and it will ensure that you have everything running there. And it also comes with a really good user interface. So you can use this interface to do everything in a way that is user friendly, and you can change everything there. And Of course, nothing is perfect. So with this robust modeling technique, you lose some kinds of readability of your model, but this is really not critical. So you can have everything there in the model. And I would like to focus on the EV reference application and the virtual vehicle composer today, because those two components are built in and come with the powertrain blockset, which provides fully assembled vehicle models for conventional, also hybrid and electric vehicles. And you also see a component library on the right, and those are here for you to simulate your engine subsystems, battery packs, or transmission assemblies. And you have many options there. So everything comes packaged for you. You can have an off-the-shelf technology built in inside Simulink. Your task is only to use it as efficiently as you can. And we will work with electric vehicle reference application. And I would like to give you a quick introduction to this model. So this represents a full electric vehicle. And you can see the drivetrain architecture on the right side of this slide. And you see that between the battery and the motor, we have electrical energy transfer. And from the motor, we have a mechanical energy output, and this mechanical energy is transferred through the gears to the differential. And from the differential, we have the output shaft to the wheels themselves. And this model is a longitudinal model. So we have 1D modeling technique, and this model is capable of doing drivetrain analysis, battery management system design and implementation. And we have also options for control and diagnostics design. And one really important thing to mention here, that this model supports hill testing. So you can embed your model on a hill hardware, such as SpeedGoat, and the model will ensure a real-time simulation for you. So this brings us to our first use case, which is battery sizing validation. The use case is that we would like to see if our battery pack is able to fulfill the system requirements of 300 kilometers range based on the VLTC Class 3 drive cycle. So you can see the VLTC Class 3 drive cycle underneath, and you see that it represents a driving profile based on time. And this time is 1,800 seconds, and we will see how the system is reacting to this drive cycle. But before we jump into the model, let's see the drivetrain parameters. So for the battery, we have the capacity of 46 kilowatt hours, and our battery pack voltage is 370 volts. This battery consists of 96 cells in series, and then we have 31 cells connected parallel. And we will see how the whole battery is reacting in this drive cycle. But vehicle, the drivetrain that we are driving with this battery pack is having the following parameters. So the weight or the mass is 1,500 kilograms, and the drivetrain configuration is a front-wheel drive system. You will see this in the model itself in a minute. So for the motor, we have a maximum torque output of 450 Newton meters, and the maximum power that we can get from the motor is 210 kilowatts. And before I open up the model, I would like to highlight that this configuration is a notional vehicle. So it's not representing any commercial vehicle that we are seeing right now on the market. So the approach is aiming to show you the process, the workflow, and you can later tailor your models to your needs. Let's jump into Simulink and let's configure this model of the electric vehicle. And to open everything, we have a really good command. So with one command, we can open up the whole project. It will put everything together for us, and it will also open the model. So you can see the model here. You can see that we have everything that we had before. And I just wanted to show you how you can open it. But I have already pre-configured one model for you. So let's explore it together. So you can see that we have the drive cycle source model block, where we are selecting the VLTP class 3. And for the parameters of the car itself and battery and the motor, we will use the passenger car subsystem. So inside the passenger car, we have the electric plant and we have the drivetrain. Inside the electric plant, we have the battery setup and the motor setup. For the battery, we are using a lithium-ion battery pack, and inside the parameters of the block, we are defining the number of cells in series. We have 96 preset, and we have the number of cells in parallel, which are 31. And we have the open circuit voltages and the internal resistance of the battery defined, the temperature breakpoints for the various temperatures of the battery. So we are having the battery model defined here. So you can see that we have a high level information of the battery. So this means that we have a system level model and we have a low fidelity, so low resolution of our model. But for component sizing, it is appropriate for us. And once I opened up the motor, you can also see the same simulation manner. So we have the maximum torque and the maximum power defined. We have also the electrical losses in the motor, and this is how we set up the whole drivetrain. And for the properties of the vehicle itself, we will use the vehicle 3-body 3 degree of freedom longitudinal model, and we have the parameters set up here. For the mass of the vehicle, we are using 1,500 kilograms, as I have already mentioned, and this is how we are reconfiguring the model. So now that we have the model and everything is ready for us, we can run the simulation. And for the simulation, I have prepared a recording for you. So you can see that we are running 1,800 seconds of simulation. The model is building, it's compiling quickly. And once we have it running, you can see that the simulation model is running much faster than real time. And this is the advantage that we have with the high resolution system level model. And you can see that after the simulation is finished, we have the results. And if we want to take a look at the results, we can do it here. So on the top left corner, you see the desired speed and actual speed of the car. And you see that the blue signal is the actual speed and the desired speed is the dashed line. And those two signals match each other. So we have a good model there, which is able to continue the speed profile. And you see on the state of charge of the battery on the top right corner that we started with 75% of charge and we ended up somewhere around 69.5%. And you see that the whole gradient of discharge rate of the battery is continuing accordingly to the speed of the car. So if we have low speeds, then the discharge rate is smaller. And for the higher velocity ranges, we have bigger discharge rates of the battery. And the battery voltage is also acting accordingly in the bottom left corner. So the voltage ranges between 375 and 340 volts. And for the range, we have driven around 23 kilometers. And you could see that how easily we were able to manage to have a reference model with the parameters that we wanted to configure, and we were able to obtain the results in a matter of minutes. And we can use those results for range calculation. And with the range calculation, we will keep it simple. So we have started with 75% of state of charge. And in the end, we had 68.6% of state of charge left. And the delta state of charge from this is 6.4%. And for the VLTP length, if we take the length, it is 23.25 kilometers to be precise. And from this, we can calculate the range of vehicle. And this was for the state of charge for 90%. And based on those 90%, we get the range of 326.95 kilometers, so almost 327 kilometers. And our aim was to reach 300 kilometers. And from this, we can see that our component sizing was appropriate, and the 46 kilowatt hours battery pack is enough for us for the 300-kilometer range with this configuration. And I think this really highlights the advantage of the model-based design, because in just a couple of minutes, we have the results and we have the range and we have everything that we needed. And I would like to continue with the second use case, which is the battery fault detection. And with this battery fault detection, we are aiming to have a simulation where in case of a cell malfunction, we will stop the vehicle. And for the requirements, we have specified the following. So if we have the temperature of one cell over 20 degrees of Celsius, we please enforce an emergency stop and stop the car. And this is what we are going to try to model. And the challenges here are the following. So we will need a detailed battery model. We could see that we had a high-level model right now, so we do not have a detailed battery model in our system. So we will also need a good battery management system, and we will need to implement a fault control. And based on this fault control, we will also do an emergency stop, and all those systems need to be implemented in our model. And this is the challenge that we are facing with this. So let's jump back to the model and let's see how we can change the model itself. So you can see that in the passenger car for the electric plant, we have one Simscape model pre-configured and one powertrain blockset. We've been using this powertrain blockset until now, but this is not detailed enough for our second use case, and we will need to activate the Simscape model. How we can use this or do this? We can do this by choosing the variant on the top level. So instead of powertrain blockset, we will use the Simscape, and with this Simscape model, we will have the Simscape electric plant pre-configured. So this is how easily we can change from one high-level, high system-level model to a detailed model. And for this model, I have configured the battery fault itself in the battery system. So inside the battery system, in the battery pack, we have for the first battery module, we have a temperature fault implemented. So what we are going to do is we are going to model an increase of temperature, and we are going to increase the temperature after 100 seconds of the first cell itself. So with this, we are going to have an unusual behavior of the battery cell itself. And this will create us the faulty signal, but we will need to have also a really good battery management system to cover this faulty cell behavior. And the battery management system, we have one state machine that is controlling the whole system. Then we have a state of charge estimation, which is estimating the actual state of charge of ours. And for the charging, we have a cell balancing logic. And in the state machine, we are monitoring the whole battery pack, and we are doing some controls for driving, charging, and standby modes. We are doing we are controlling the inverter and the charger states of the battery, but most importantly, we are also doing fault monitoring. In the fault monitoring, we are monitoring the cell temperatures, and it behaves as in the following manner. So when we have no temperature fault, then we are in this state. And when the maximum cell temperature is higher than the temperature limit, then we will have a signal of high temperature becoming true. So this shows us that we have a faulty signal there and a faulty temperature. And also on the other hand, for the minimum cell temperatures, if it's lower than the temperature limit of the low temperature limit, we will again have a low temperature limit faulty signal showed and sent to the control systems. And with this, we have the fault monitoring implemented, but we also need to do an emergency stop. And for this, we are going to use this implemented emergency stop block. And what we have there is based on the following. Based on the high temperature signal, if it's bigger than 0, so it's true, then we will switch from the test cycle temperature, or not temperature, but driving profile to the 0 kilometers per hour speed, and we will do an emergency stop, and we will force the car to stop. So we have implemented the emergency stop. In the controllers, we have the cell fault monitoring system implemented, and in the passenger car, we have the whole fault mechanism implemented. But let's see how it is behaving while the simulation is running. So you can see that we are running 400 seconds of simulation, and once the model is built, is running, then we are able to monitor the signals. So on the top figure, you see the battery cell temperatures, and you see that after 100 seconds, one cell temperature starting to rise, and it rises up to 52 degrees Celsius, and this is when the whole temperature signal, fault signal, is becoming active, and we are stopping the car itself. So this is how we are preventing a fire or a battery explosion, and this is how we are saving the whole battery pack for our signal or our model. And if we take a look at the results, again, you can see that we have reached the temperature of 50 degrees Celsius for the cell 1 at around 250 seconds. And in the bottom left corner, you see that at the same time, when we reached the 50 degrees of Celsius, then we were able to stop the car, and we have prevented an emergency status of the car. So with this, I wanted to highlight how you can manage to model a detailed system, such as a battery cell temperature, and how you could control the whole system as a whole, and how you could prevent an emergency system. And to wrap up the presentation, I want to highlight everything that we went through. So first, we talked about the challenges of drivetrain electrification, and then I have shown you the electric drivetrain modeling options in Simulink. There we covered the electric vehicle reference application, and we used that model for two use cases. Once we have showed an electric vehicle battery modeling use case and a battery management system use case for the battery fault detection. And with this, I would like to highlight the advantages of model-based design and how easily we could do the modeling and the battery management system implementation of our systems.